This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Okay, so this is the last, today we're going to talk about moment of inertia. This is the last bit on this little topic. After this, we're going to do the last section of the course, which is nice and straightforward, something easy to finish off with. So we've talked about volumes and areas on Friday. On Monday, we talked about centres of mass, so finding like the centre of something where it will spin and rotate nicely. Today, we're going to talk about moments of inertia. So when you're talking about, you guys are probably all done or doing mechanics or something like that, right? So when something is moving in a straight line, it has some inertia, which depends on how fast it's going, and it also depends on how heavy it is, right? And that inertia will tell you about how hard it is to stop this thing, okay? So that's in a straight line. If you've got something that's spinning, it's not just inertia, it's called moment of inertia. And these things are really important, okay? When the wheels of a car are spinning, they've got inertia. On a flywheel, that's got inertia. On a turbine, that's got some moment of inertia. So you want to know how hard is it to start these things rotating and how hard is it to stop them rotating, okay? The other use for this sort of thing is it helps us to calculate the energy, rotation energy, okay? If you have a look here, here's the kinetic energy of rotation, and if you think about it, this is the moment of inertia and this is the angular velocity or angular speed. If you think about it, you know when you're calculating kinetic energy for something in a straight line, it's just like a half mv squared. So this is kind of the same, but it's a rotating thing, okay? Just like a half mv squared. All right, so we're going to talk about how to calculate this I thing, which is useful for those kinds of reasons. Okay, here's the definition here. The moment of inertia, remember we're thinking about the integral as a sum, and remember we're thinking about the d as meaning a little, okay? So we've got the sum of all the little masses in the body, and when we're doing it, we're multiplying it by the distance from the axis of rotation squared, okay? So if you have a small mass, you're not going to make much contribution, or if you are close to the axis of rotation, you're not going to make much contribution. If you're far from the axis of rotation, you're going to make more contribution to the momentum, okay? And you'll know that from things like, oh, I don't know, what could you spin around? Pardon? Yeah, well, yeah, you could spin around a merry-go-round, but if I'm trying to think, what would you spin with your finger that's really short, and then you could spin something longer, right? And you know that that's something that's got the mass right heavy at the end is going to be harder to stop than something as little just spinning around, okay? So if you're further away, you have more contribution. If you're heavier, you have more contribution. So we're summing up all the little masses multiplied by their distance from the axis squared. Okay. Now, because, or in this course at least, we're going to be talking about constant density, that means from this mass we can whip out that density and we're going to have a volume left over. So this is the formula that we're going to be using for three-dimensional things. Okay, we're going to times by the density because that's the constant that's come through the integration sign, the distance from the axis squared, and sum up all the little volumes. So here's a little picture of a little volume, and here's its distance from the axis. And we want to sum this up for all of these things in this little drum thing, okay? If you're talking about something that's flat, like a flat wheel spinning around, okay, then instead of the density, you've got the areal density. So you've got, instead of the density per unit volume, you've got the density per unit area. And then you don't want to sum over the volumes, the little volumes, you want to sum over the little areas, okay? But it's the same formula, but written in 2 dimensions instead of 3 dimensions. Okay, now just like we talked about for the other things, this first one is a 3-dimensional integral and the second one is a 2-dimensional integral, and we don't do them in this course. Okay, so we need to figure out a way to change this into a 1-dimensional integral so that we can do it. Okay, that's what it says here, and then I've just realised there's no picture of it. Okay, so what you want to do, what do we want to look at? Here. Okay, when you're calculating this part here, or this part here, right, you can write the little volume in lots of different ways, as we did before. This one here, this distance from the x-axis, you only have one way to write this. It's the distance here. And so when you write this, you only get one choice. When you write this one, you have to write it so that it matches with this one. Okay? So if you're summing up an integral, if you're summing up all the little pieces, let's look at this picture before we do it, shall we? If we're doing this one here, right, we could, this is a flat little sheet, right, imagine, and it's held at one end, and then it's going to be rotating around. If I dislocate my elbow, like this, okay, a flat little sheet, like maybe one of those clicker things that you get at the show and drive everyone nuts. Okay, one of those things here. Now, if you're just looking at this flat sheet, you could slice it vertically like this, or you could slice it horizontally like this. The important thing is when you're doing these ones is you have to choose to slice it. You have to slice it, you don't get to choose. You have to slice it so that everywhere in one slice is the same distance from the axis of rotation. Okay? Now have a think. If we slice it this way, all the points in here are this distance from the axis of rotation, right? And if I take another slice further closer to the end, all the points in this slice are this distance away from the axis of rotation, okay? So this problem, you have to slice it vertically, all right? Actually, let me go to the piece of paper and then I can point better. Okay, if you had sliced it horizontally, right, let's just draw a little picture up here. If you slice it horizontally, right, this point in the slice is that far away from the axis of rotation. This point is that far away from the axis of rotation. This point is that far away. So all these points are different distances away from the axis of rotation. You can't slice it like that. You have to slice it like that. Does that make sense? Yeah? Okay. And that's because you want to write down this L, and it should be the same for everywhere in that one slice. Okay? All right, so let's do this example then, straight away. Okay, calculate the moment of inertia of a rectangular plane sheet rotating about an axis along one side of the rectangle. So just like those clickers that you get at the show and drive everyone nuts. You guys, can you be quiet please, because that's coming right down here. Okay, so we're going to slice it vertically. Let's write this down, slice. Oops. Okay. All right, so that's what we're going to do. Slice parallel to the axis of rotation so that everywhere within one slice has the same L. Okay? Because when we want to integrate, we're going to sum up the slices, right? So each slice has to have the same properties within that slice. Okay. Slice vertically. Okay, when we slice it vertically, these little slices are going to be rectangles. Okay, so rectangles, they're pretty easy to deal with. I equals rho okay, and it's flat, so we're going to use the areal density, although I haven't given a subscript A, the areal density, and we're going to sum up the little areas. Okay, so to make this integral something we can do, we need to figure out what this A is, dA, and what this L is. Okay, so that's what we're going to do on the side here. Alright, the little areas are rectangles, and when you find the area of a rectangle, you just do the base times the height. Okay, so the height here is easy. What's the height? B, beautiful. And what's the width? dx, beautiful. Taylor, if you can answer this, you can have a lolly. Alright, what is the distance of that slice from the axis of rotation? What's the distance from the axis of rotation of this slice? This distance here. You have to tell it to me. It's a function of x, so you can tell it to me in terms of x. Does anyone know? This distance here, what's this distance here going to be in terms of x? It's just x. Right? This slice is at position x. Right? This slice is at position x. At position x it has height b, width dx, and we're at position x. Okay? It's just x. That's it. Alright. So now we just have to plug everything in. L squared is going to be x squared. dA is going to be b dx. Okay, and we're integrating in the x direction. So what's the smallest x and what's the biggest x? 0 and a. Beautiful. Going from 0 to a. That's it. So this is an integral that we can do because we are mathematicians. The b can come out the front. That's just a constant. 0 to a. Oops. Let's just write this nicely. 1/3 rho a cubed b. Oh, nearly going off. That's it, that's the answer. So that's the moment of inertia. You can figure this out if you've got one of those clickers. Looking for something extra fun to do, you can figure out the moment of inertia. Alright, for a reason that will become clear later on, but is not now, the total mass, I'm just going to rewrite this in a different way so that we can use it later on, okay? The total mass of this thing is going to be its area times its density, right? So that's going to be rho times A times by B. And if that's rho times A times B, it means that I can write this in terms of the mass. Okay? This is a perfectly fine answer. This is the answer I'm looking for in an assignment or something. I'm just writing it this way so that we can use it later on in this lecture for something else. Okay, so 1/3 of the mass times by a squared, the length squared. Okay, does anyone have any questions on that one? No? Let me just check. Okay. Alright, in the notes there's some stuff that talks about how to calculate the moment of inertia of a rod that's spinning around. So you can imagine if I got this and made it skinnier and skinnier and skinnier, it would be like a rod, okay? And that's an important application as well, but that's just a discussion and I'm not going to go through that. What I am going to do is just go on to the next example. I'll do a couple of more ones, a couple more. I can turn the page. Okay. Consider a disc of radius A spun about the z-axis through its centre perpendicular to the plane of the disc. Okay, so think about what's happening here. This is a disc, it's not a sphere, it's a flat disc, right? And we've got an axis going through the centre of the disc perpendicular to the plane of the disc, and we're spinning it around. Okay, so this is like a tarzo. You guys too young for tarzos? No? Okay. I'm like, am I really showing my age? Okay, so it's like a tarzo, right? An axis going through and you're spinning it around. Okay. As with all of these problems, the first thing to do is decide how to cut it. And look, I've kind of already told us already. What you have to do is you have to cut it so that everywhere within one slice is the same distance from the axis of rotation. Okay? So think about the ways you could cut this. You could cut it horizontally like this. If you cut it like that, let's go up here again. Oh, that's terrible. All right, if I cut it like this, right, this point here is that far away from the axis, and this point here is that far away from the axis, okay? And they're not the same, All right, so you can't cut it like that. And the same, if you took a vertical slice, you'll get the same kind of thing, okay? It's a different distance from here to there as it is from there to there, and so you can't cut it like that. You have to cut it so that everywhere within one slice is the same distance from the axis of rotation. So for this problem, it's got to be in little annular circles, okay? All right. Cut into annular slices. All right. So now we've got this flat annular slice. If we just take one of those little slices, we've got a little thin annulus. How are we going to find the area of that? Actually, let's write down the equation for that first. I equals rho L squared dA. Now it's going to be a function of r because each one changes depending on how far out you are, okay? All right, so how are we going to find the area of one of these little slices? Any ideas? What do we do? Think. Yes, Kevin?
You just use the area of the circle formula, so pi r squared.
If you use the area of the circle, okay, the area of a circle, but we only want this part of it.
Use the circumference and measure the length.
Beautiful. And so if we use that one, right, we know this width here, but we kind of don't know it's a bit hard to know the difference between them. So what you do is exactly that. You get out your scissors, snip, snip, snip. You've got this little disc thing here, snip it up and spread it out. And then you're going to have like a long strip. All right, now there are going to be these little triangles at the corners. Bless you. Bless you, bless you. There are going to be these little triangles at the ends, right? But these are second order infinitesimals, second order small, so we're not going to count them, okay? So now we just need to know the area of this rectangle. We can do rectangles. This distance is dr, and this length, just like Mark said, is going to be the circumference, 2 pi r. Okay? You can have a lolly for that, Mark. Snip it up. It's going to be the circumference, 2 pi r. All right. dA, and it's a function of r, is 2 pi r dr. Okay. 2 pi r for the area, and the distance, from the axis of rotation is going to be what? How far away is this slice from the axis of rotation? Ah, beautiful. That's right. It's just distance r. Now I've got this, now I've got this. We just need our bounds, but let's just do that in a moment. All right, L squared is r squared, 2 pi r dr. All right, bounds on integration. We're integrating with respect to r. What's the smallest radius of these little circles and the biggest radius? Yep, the biggest. It's going to be A, right? A. So from 0 to A. All right, here's an integral we can do. 2 pi rho. This is just r cubed, right? Oops, sorry. Quarter r to the 4. What does it equal? Pi over 2 rho a to the 4. That's it. Okay, does anybody want to ask any questions on that one? No? Okay, once again, for reasons which will become clear later, I'm going to write this in terms of its mass. Right, so the mass of this thing here would be the area times the density, right? So it's pi r squared times the density, rho. Now let's have a look. A rho and an a squared and a pi, that's going to be a half ma squared. Half ma squared. Okay. What next? Okay, is everyone done? I think so. All right, another example here. So the disc of the last example spun about an axis through its centre in the plane of the disc. Okay, so what's going on here? Here's something my grandpa used to do to scare me when I was little. He used to get an envelope and he used to get a piece of wire and bend it so it was making like a U shape, and then he'd get a rubber band and put it between the top of the U, and then he'd get a button. I don't know how he'd attach it to the rubber band, but it would be attached to the rubber band. And then he'd wind the button up, right, round and round, put it in an envelope, and then he'd give me the envelope, and you open the envelope and the button spins around hitting the paper and it makes this crazy noise. And when you're 3, it really scares her. Okay, so that's what's going on here, right? We've got a disc like this button and it's spinning around on its axis like this, okay? And we want to find out the moment of inertia, okay? That's what's going on. Oh, look, I've given us the answers again. All right. So we have to slice this in such a way that everywhere in one slice is the same distance from the axis of rotation. Okay. Now in this case here, here's the axis of rotation here. So everywhere in a slice has to be the same distance from this. Okay, and I've already given the answer. The answer is going to be a horizontal slice like this, okay, because here you're that far away, here you're that far away, here you're that far away. It's always the same, okay. If I took annular slices, that'd all be different distances from that x-axis. If I took a vertical slice, that'd all be different distances from that x-axis, okay. Does that make sense? This is one of the most important parts of these problems, right, is deciding how to slice them, okay? So make sure you understand why we're slicing them in these ways, all right? If you don't, stick your hand up or come and see me. All right. Slice. Horizontally. Okay, so these things are rectangles. Almost rectangles. Okay, the thickness here is dy, and then we need to find out the length. That's right. Yeah, ha ha ha. But it's going to be 2 times that, right? Yes. All right, rho. Add up everything, L squared. Now it's a flat thing, so it's dA. And the area of these slices depends on the height where you are, right? Because at the top you're going to get a short little slice. In the middle you're going to get a long one. At the bottom you're going to get a short one again. Okay, so it depends on where you are, so it's a function of y. Alright, dA is a function of y equals. Okay, now if this one hadn't been here, right, we didn't know the answer, I would have said that the length of this rectangle is going to be 2 times by x, right? Here is a point here that's coordinates x and y. Okay, so this distance here I would have said was 2x. Okay, and then I would have said the area of this rectangle is 2 times x times dy. And now we have to find a relationship between x and y, because you can't, I mean the 2 is fine, that's a constant, right? We're going to integrate this with respect to y, so this x better be turned into y somehow. Okay, so the way to do that is either with the equation of a circle, because the equation of a circle is going to be x squared plus y squared is a squared, or you can use Pythagoras on this little triangle here. Okay? Pythagoras and the equation of a circle, they're the same thing. Okay, does anyone want to ask any questions about that? No? All right. Now we want x, not x squared, so that's why the square root's there. A squared take y squared dy. Okay, so that's this one. We also need the L. Okay, so how far is this slice from the axis of rotation? Beautiful, it's y. Y. Okay, we've got this. We just need the bounds. Let's do that in a moment. Rho y squared times 2 okay, we're integrating in the y direction, right, because we've got a dy. What's the smallest y and what's the biggest y?
Negative 8.
Beautiful, negative 8a. You can have a lolly, Taylor, you've answered lots now. Necklace. Oh, just. Okay. Squared. Okay, so we've got an integral here with respect to y. How are we going to integrate this one? Think. Start with the easy way. Can we just do it? Can you do a u substitution? No, you can't. That's right. Because here, the derivative of this one here would be a y, and we've got a y squared, right? We've got too many y's hanging around. All right, the next thing, what's the next thing on the list? I can't even remember. Integration by parts, when you've got two things added together. Yeah, I'm just thinking about integration by parts. I think you could, I'm not sure if you could do it by integration of parts or not. But yes, trig substitution is how we're going to do it. That's exactly right, okay? Because we've got, here is our little trig equation here that we're going to use. So that's the way we're going to do it. Now, I don't have all those 6 equations on the board. They're on your cheat sheet for the exam, right? So we're going to use a squared take a squared sine squared theta. That's the one we're going to use. Okay? So this one here is matching up with the a squared. The minus and the minus match. That means that y squared has to match with a sine squared. So y has to be a sine theta. Okay, everyone dredge the memory banks. This is how you do it. Okay, we also need to, so that's going to replace this bit here, and we can use this to do the y squared. We also need the dy, d theta, pardon me. What else do we need? The bounds, we can either leave them in terms of y or we can change them to thetas. I'm going to change them to thetas. When what? When y is equal to minus a equals a sine theta minus 1 sine theta. Just hang on a minute. Okay, sine theta is equal to minus 1. Now think about sine theta. Right, sine theta goes like this. Okay, remember when we're finding the inverse though, we have to chop it so that it's 1 to 1, and we chopped it like this, right? So we're only using this middle part here. So when is sine equal to minus 1? Minus pi on 2. Yeah? Using up the whole page here on the right hand side. All right. When y equals a, theta is equal to pi on 2. Okay, so now we're set, I think. Equals 2 rho minus pi on 2 pi on 2. Y squared is going to be a squared sine squared theta a squared minus y squared, that's this here, right? A squared minus, and this is y squared. So I can replace this whole bunch of stuff under here by a squared cos squared, and then I'm going to take the square root. A cos. Is everyone happy with that? Did a couple of things at once. Okay, and now the dy is this stuff here. A cos theta d theta. Oh, we've taken those 4 a's out, right? What have we got? Sine squared theta, cos squared theta, d theta. Sine squared theta, cos squared theta. Okay, how are we going to integrate this one? Any ideas? Yeah, there's a trig identity for it. So this is the one where you want to use the double angle formula for this one and the double angle formula for this one. Okay, so I'm going to write them down. Okay, so we're going to do sine squared and change it into this, and a cos squared and change it into this. Alright, so we've got 2a to the 4 rho. Now, if I do this one times this one, I'm going to get a quarter from those things at the front, right? That's a constant, so I'm going to zip that through the integral sign. Okay, now get to the business part of it. Alright, if I multiply these two things together, this is like the difference between two squares, right? This one's the same, this one's the same, so it's the difference between two squares. So I can write that straight away as 1 minus cos squared 2 theta. Okay. Alright, can we integrate this? No, how are we going to integrate this one? Going to do this one again, right? The double angle formula again. So we've got a 2 theta here, that's going to give us a 4 theta over here. And then we're going to be able to integrate it because then there's no squareds anymore. So this is a half rho 1 minus this thing here. So that's minus a half cos 4 theta, right? Because you have to double the angle that you started with. Does anyone want to ask any questions so far? You're allowed to interrupt, that's okay. Okay, so we can integrate this and this, so we can join them together and just get a half. We can integrate those two, we can integrate this one. Now at last we can do something. Brackets. So this gives me a half, so that's going to be a half theta minus a half for this 1/2 here. Right, now we have to integrate cos of 4 theta. That's going to go and turn into a sine of 4 theta. Okay. When we differentiate this, just let's check. I'm going to differentiate it to make sure I get this one. If I differentiate this, I would get cos 4 theta and I'd get a 4 coming out the front. Okay, I don't want a 4 out the front, so I'm going to put a quarter. And the sign doesn't change, so that's fine. Okay. Nearly done. Nearly done. All we have to do is substitute in, and pi on 2 gives us some nice numbers, right? Okay, so pi on 2, put that into here and gives me pi over 4 minus 1 over 8 minus plus pi over 4 plus 1/8 sine 4 times pi minus pi over 2. Okay. 4 times pi over 2, that's 2 pi, right? And sine of 2 pi, oh, it starts here. That's funny, it looks like a bunch of axes now. Sine of 2 pi is here, right? So it's 0. This one's 0. And this would be sine of minus 2 pi, so that's 0 as well. So we're nearly done. Okay, does anyone want to ask any questions about that one? No? All right. We're going to do one more example before the break, and we might be a bit late, but I'll still give you 10 minutes to go and stretch your legs, okay? But we'll get one more in before the break. Loads of examples. Okay. Oh look, I've told us the answers again. Okay, consider a sphere rotating about the z-axis through its centre. I'll even tell you how to do it in the question. By slicing the sphere into annular cylinders, find its moment of inertia. Okay, so we've got a ball and it's spinning on it's just spinning on the spot, like if you've got a basketball spinning on your finger. Okay, if you're aiming for the Globetrotters, that's what you can do. Okay, spin a basketball on its top, on its bottom, whatever. So if you look from the top of the sphere, right, if you look at the top of the basketball spinning around, you're looking straight down the axis of rotation, and you want to slice this thing so that everywhere in one slice, all the points are from the same distance from the axis of rotation. Okay, so if you look at it from above, looking down the cylinder, you want to take annular looking down the sphere, you want to take annular slices. Okay, so get out your little scone cutter and then get a smaller scone cutter and a smaller one. Okay, so you've got these annular slices coming off. All right, so they're going to be like little cylinders, like little cylindrical shells, let's say that. Okay, so here's a view from the top. If you look at it from the side, you can see that you've sliced it like this. So here's the side of a cylinder, top and bottom. So the outside slices are going to be very short but very big cylinders, and the inside slices are going to be very small but very tall ones. Okay, does that make sense to everybody? Hopefully. Okay. Slice. Okay. So we have dV this time, because it's a volume, not an area. Alright, so one of these little cylinders looks like this, and it's got some thickness. Oh, look at my drawing skills. The thickness is dr. Okay, a little change in the radius of the cylinder, little change in the radius. The radius of these things, well, let's just call it r. And the height of these things, let's just call it h, and we'll figure it out in a minute. All right, so how are we going to find the little volume of one of these cylinders? Beautiful. We're going to get the scissors out, we're going to cut it, and we're going to lay it flat. Because then we've got a rectangle. We know what to do with rectangles. Okay, so it's got thickness of dr. The height of this thing is h. Let's figure that out in a minute. This distance here is going to be what? Beautiful. The circumference of that cylinder, so it's 2 pi r. Okay? Alright, so we want to know the little volume. dVr is equal to, well, it's just a rectangular prism thing, right? So 2 pi r h dr. Multiply them all together. Okay, this is telling us that we're integrating with respect to r, so everything better be in terms of r. The 2 and the pi are okay because they're constants. The r, that's fine. Okay, the h is the one that we've got problems with. And look, I've given us the answer. Okay, so this is the height of your cylinder, right? If I draw a little triangle here, this thing here is a because it's the radius of the sphere. It's always going to be a. Even for a short cylinder, it's like that. It's still a. For a tall cylinder, it's still a. This is the radius. This distance here is the radius of the cylinder. So this is our r. And this is the distance that we care about. Actually, we care about the whole distance. So the whole distance will be twice of this distance. Okay, and you can do a little Pythagoras on this little triangle here and say that this distance here is the square root of a squared take r squared, and then we want twice of that. Okay? Is everyone happy with that? Yeah? Okay, that's going to be h. 2 pi r times by 2 square root a squared take r squared dr. Okay. And what else do we need? We need L. Okay, so if you have a slice like this, a little annular cylinder, how far away are all those points from the axis of rotation? R, beautiful. They're going to be r away. That's right. Okay. Rho r. Now don't forget to square it, right? Because it's L squared times by 4 pi r square root a squared take r squared dr. Okay. Now, if you can tell me the bounds of integration, you can have it, Ollie. We're integrating with respect to r, so the smallest radius is, the biggest radius is, not x. Beautiful. Okay. The radius of the sphere. Okay, so we're integrating from 0. That's the tallest, skinniest cylinder. The biggest, fattest, shortest cylinder is going to be A. That's it. All right, this looks a bit trickier, doesn't it? 4 pi rho r cubed all right. This is a tricky one. It is going to be a U substitution. What's going to be the U? A squared take R squared. A squared take R squared. Let me just see. Yeah, let's do it like that. Yep. You can do U is A squared take R squared, or in this question you can actually do U is the square root of A squared take R squared. Okay, and it's not obvious how, but I'll show you how. So this is a little bit tricky, this one. It's probably too tricky for an exam, but probably tricky enough for an assignment because you can think about it. Alright, let U equal A squared take R squared. You could also do it with the trig substitution, I reckon. I haven't done it with a trig substitution, but I reckon you could. Okay, dr is equal to minus 2r dr. Okay, now let's think about this. Here's r dr, and here's dr, and here's 3 r's, right? So one of these r's is going to get used up here. we've still got 2 left over. Okay, let me just do this. Minus a half dr equals r dr. One of them is going to get used up here. We've still got 2 left over. We need to turn those 2 into a u. How are we going to do that? Yeah, we're going to use this again. Okay, so r squared is equal to what? A squared take u squared. Okay. All right. 4 pi rho. Let's deal with the bounds in a moment. Okay. R cubed, one of those is going to get used up in the du. 2 of them are going to get turned into this. A squared take u squared. This thing here gets turned into the square root of u. The dr plus one of these r's is going to get turned into minus a half dr. Oops, no, that's not right. That's a u. Oh, what have I done? Crikey. It's Friday, that's my only excuse. U.
Where your r squared equals a squared take u squared, where does the square come in?
Oh, it doesn't. Oh, far out. Send me home. Okay. Have we got everything right now? I think so. Okay. All right. Good. All right. Now bounds on integration. So remember we can leave these as r bounds, but we have to write r equals, or we can change them to u's. I'm going to change them to u's. So r equals 0 means that u is equal to a squared. Oops, running out of space. And r is equal to a means that u is equal to 0. Okay, so this is one of those questions where it looks like we've got the bounds upside down, but we've got a minus sign here to kind of cancel each other out. Okay? Equals. Right, I'm going to take this a half out the front. Minus 2 pi rho. Okay, so now we have to integrate with respect to u. Integrate with respect to u this palaver here. How are we going to do that? Think, can we just do it? What if we expand out these brackets? Then all of a sudden it's really easy, right? So we get a squared square root of u minus u to the 3 halves. Bracket, bracket, du. Okay, now this is just like different powers of u, so we can integrate that. We know how to do that from long ago. Alright, so u here will get a squared u to the 3 over 2, 2 over 3. Okay, minus u to the 5 over 2, 2 over 5, a squared 0. Okay, now if we put u is equal to 0 in here, we get 0. U is equal to 0, we get 0. U is equal to a squared. U is equal to a squared, pop that in here. This squared here and this a half here are going to cancel out, and we're going to get a cubed plus 2 over 5 a to the power of 5. Okay, equals. Okay, these are both a to the power of 5, so that's a good thing because they've got the same kind of units. 2/5 minus 2/3. Oh, that's too hard. 2/5, what's that? 6, 15 minus times by 5, 10, 15 minus 4, 15. A to the 5. Okay, almost there. Look how late we are, 10 minutes late. Okay, now just like I did in the other ones, but for no apparent reason at the moment, the mass of this sphere is going to be 4/3 pi r cubed, but this time it's A times the density. Right, so I'm just going to rewrite this in terms of the mass. Equals the rho, the pi, so there's going to be 2 of those left over, and there's going to be 2/5 ma squared. Okay, and we're done. All right. Does anyone want to ask any questions? No? Okay. Let's have a 10-minute break, and we're super late, so we'll come back, well, it's 8 past. We'll come back just before 20 past.